In this lecture, we'll talk about entropy. So, the one-way character of irreversible process is so universal that we take it for granted. If these processes were to occur spontaneously in the wrong way, we would be astonished. Yet none of these wrong way events would violate the law of conservation of energy. For example, if you were to wrap your hands around a cup of hot coffee, you would be surprised if your hands got cooler and the cup got warmer. That is obviously the wrong way for the energy transfer. But the total energy of the closed system, which is made up of your hands and the cup of coffee, would be the same as the total energy if the process had run in the right way. Another example could be, if you popped a helium balloon, you would be astonished if later all the helium molecules were to gather together in the original space of the balloon. That's obviously the wrong way for molecules to spread. But the total energy of the closed system, the molecules plus the room, would be the same as for the right way. There are numerous examples. We live in a world of irreversible processes, right? Thus, changes in energy within a closed system do not set the direction of irreversible processes. Rather, the direction is set by another property that we shall discuss in this chapter. That property, we call it entropy, and we will talk in this chapter about the change in entropy. Entropy has a symbol, we'll use S. And we'll see later, the SI unit of entropy is Joule per Kelvin. Here we can make a postulate, we can call it entropy postulate, that if an irreversible process occurs in a closed system, the entropy S of the system always increases, it never decreases. Let's look at the free expansion of an ideal gas. We have taken this example before in earlier discussion. So let's say here, this figure, in these two figures, we see the gas is in its initial equilibrium state I, confined by a closed stopcock. This is stopcock to the left of the thermally insulated container. So this thermally insulated container, all the gas molecules are in this container. This is a vacuum. If we open this stopcock, the gas rushes to fill the entire container, right? Eventually reaching the final equilibrium state. Let's call it F. This is an irreversible process. That means there is nothing you can do, or minor changes in the equilibrium position you can do, so that all the molecules by itself, that's very key, or spontaneously is the word, can go back to this chamber and stay there, right? So this is an irreversible process. All the molecules of the gas will never return to the left of the container, right? If I have to plot PV plot of this process, then here, let's say this is my pressure and volume. We have seen that, and then we say, okay, in the beginning, let's say this is my starting initial position. So I can say this is my initial state of pressure and volume, and let's say as it gets distributed into both chambers, let's say this is my final. So pressure decreases, volume increases, right? Good. So this is just this is an irreversible process, right? So now let's talk about this diagram here, and let's say here we are trying to get a reversible isothermal expansion. So let's say we confine the gas to an insulated cylinder that rests on a thermal reservoir maintained at some temperature T. So this is my thermal reservoir, and molecules are confined in this insulated container cylinder. We begin by placing just enough lead shards. So these are my lead shards. Begin enough lead shards so that the initial pressure and volume of the gas are those of the initial state I. So we create the condition by putting some lead shards so that the initial value is same as the here. Okay, now we start removing this lead shards slowly, piece by piece. We take piece by piece until the pressure and volume of the gas are those of the final state F. So we get those final state F. All right. The temperature of the gas does not change because the gas remains in thermal equilibrium with the reservoir throughout the process. The reversible isothermal expansion of this figure is physically quite different from the irreversible free expansion of this figure, right? However, both processes have the same initial and final state, thus must have the same change in entropy. Here we um, at this stage we assume the entropy is a state property. That means it only depends on the initial and final state of it. Because we remove the lead shard slowly, the intermediate states of the gas are equilibrium states. So we can plot them on the PV diagram, and it will because we went slowly and they're in thermal equilibrium, so we can on each stage, as we remove, let's say, one shot, at each point we knew the exact pressure and volume, so we can plot, and so we know how pressure varied. So all we know the pressure volume curve, right? Entropy can be defined as a measure of a disorder of a thermodynamic system. In the previous example, since volume is more, the molecules have more disorders. They can move more randomly, right? Delta S is, we can define as, is a change in entropy, right? Positive delta S means that there is increase in entropy. That means there is increase in entropy. That means there is increase in the disorder. Let's talk about an infinitesimal isothermal expansion of an ideal gas. So positive change in entropy will means that increase in entropy, which in turn means there's increase in disorder, right? So consider an infinitesimal isothermal expansion of an ideal gas. So since this is isothermal, that means delta change in internal energy, we have seen earlier, internal energy must be equal to 0, right? So using the first law, we can see that dq is equal to dw is equal to p r dv, p times change in volume, or we can say ideal gas law. So p is nothing but nRT divided by v. So replacing p for this, and this goes like this as it is, right? So now let me right? So we can rearrange this equation as dV over V is equal to dQ over nRT. If you look at this equation here, the gas is more disorder after the expansion, right? So more is dV, the more is the disorder. The molecules are moving in a larger volume and have more randomness of position. Thus, dV over V is a measure of the increase in disorder, and the equation shows here the dV over V is proportional to dQ over T, right? N and R being constant for a given amount of gas, right? So I can make this dV over V as my change in entropy and take the constant as 1, and we can say this is dq over t. So this is the first mathematical relationship between the change in entropy and amount of energy supplied and at a temperature T, right? So this is for infinitesimal entropy change ds during an infinitesimal reversible process at T. If the total amount of heat Q is added during a reversible isothermal process at absolute temperature T, then we can say that delta S is equal to Q over T, right? And remember, delta S is always entropy final minus entropy initial. So this equation is a general equation we found at a constant temperature though, right? For a reversible isothermal process. And here, from here, we can say the SI unit of entropy is joule, Q is heat, over Kelvin. Okay. So delta S is equal to Q over T for a reversible isothermal process. How will that equation look if my temperature is not a constant temperature but changing? So each step we can change in a smaller step. So I can say delta S is dq over T, and we can integrate, we can add all those small steps. So let's say this is my initial state and this is my final state. So this one is when it's reversible but temperature is changing. So when this temperature or we can say changing temperature process, changing temperature process. All right, so we have to integrate the whole term. Here we can also say when the temperature change delta T of a system is small, right, to the temperature before and after this process, the entropy change can be approximated as, so we can also write delta S is Q over T average, right? So that's kind of, so if there is a little change from initial and after, then we can just take the average temperature. So what is T average? T average is equal to average temperature of the system, average temperature of the system during the process. Good. So that concludes our entropy lecture. Great. Thank you.